Okay, so I'm going to cover some of the material at the beginning of Chapter 1 of the Headland Strength Materials book, Mechanics Materials book. Most of this stuff is review of statics. And again, just as a reminder, as I mentioned, the syllabus about these lectures, I'm not going to really focus on doing problems. I'm more going to do the one directional lecturing type of stuff where I talk to you and reserve the problems where we can have two-way communications with the class. So what I wanted to talk about in this class is the equations of equilibrium. I'm writing a name. Excuse a sloppy image. Okay, so we're going to talk about equilibrium equations. These are the most common used thing in this class. And when we talk about the equations of equilibrium, we'll talk about them in vector form and in scalar form. The vector form is sort of a 3D form, and scalar is stuff we do when we kind of simplify the problem to 2D or even 1D. We'll talk about computing moments, moment vectors. And then something that's really important, and the book doesn't get into too much, although you should have seen a good deal of this in statics, is discussion of free body diagrams. All right? So free body diagrams are, if you have the ability to be comfortable writing equations of equilibrium, you're also comfortable drawing correct and clear free body diagrams, you'll have a much easier time in this class. If you struggle with this, I guarantee you it will only hurt you in this class. So I cannot emphasize enough the need to be able to draw correct free body diagrams. I'll talk about what's a correct free body diagram. Okay? All right. So this is a class that's based on statics. The bodies are not in motion, or they're moving so slowly that we can assume them to be in equilibrium. So when we talk about equilibrium, this is the situation where the acceleration is equal to zero. Okay? So very often, this is going to be situations where the velocity is zero. The body is not moving at all. It's fixed. But that's not the only situation. This also can include the situation where the velocity is constant. Okay? And we'll see situations like this when we do torsional problems and rotary motion. So, for example, if you have a shaft that's rotating, you might have a torque that does that, right? But the body is rotating with a constant angular velocity, right? So velocity is constant. That's still an equilibrium body. Okay? So both these situations are taken into account from the equation. Okay. So first, let me do the vector equations of equilibrium. So we have some body. Okay? Looks like that. And there might be some forces applied onto it. Point forces, or also distributed loads. Now remember from statics that you can also consider an equivalent point load from a distributed load, right? And there might also be some moments that are applied. Right? I will draw moment vectors with two arrows, okay, to differentiate the force. This is all defined in some coordinate system. X, Y, Z is what we commonly use. And the equilibrium equations are two vector equations. First one is vector sum of forces is equal to 0. And the second one is the vector sum of moments. All right? So I put the little wiggle under here to denote that it's a vector equation. Now, that implies 3 scalar equations. Sum of forces in the x equal to 0, sum of forces in the y direction equal to 0, and sum of forces in the z direction equal to 0. And likewise, this implies 3 scalar equations. Sum of moments of the x-axis equal to 0, sum of moments of the y-axis equal to 0, and sum of moments of the z-axis equal to 0. Let me just make a couple of points. I'm a little stickler on notation. I think we have good notation. It makes your life easier and helps sort of, the problems to fall apart. So you notice I keep the wiggles under things that are vectors, and if it's not a vector, I don't put a wiggle under it. The other thing to remember is when we talk about sum of moments, they have to be with respect to a point. So you have to take the sum of moments about a point. Maybe it's point O. It could be any point in the body. But if you try to do, again, maybe sum of forces around another point, this set of equations is linearly dependent with the other set of equations. So it gives you no new information. So this, once you do sum of moments about a point for a body, you really should not do sum of moments around different points. It will not give you any more information. I guess there are probably some situations where we have done. Okay? So these are vector equations of equilibrium. So in 3D, they're kind of nice. A lot of problems we'll do in this class are two-dimensional problems or one-dimensional problems, and we'll talk about those. But let's talk about 3D first. You've actually seen this stuff in statics as well. So a real simple example is, let's say we have a bent piece of tubing. That's supposed to be a solid tubing. Maybe it's fixed to a wall at one end. We'll call this point A. Let's give it a coordinate system. So let's call this the x direction. This is the y direction. This is the z direction. Right? And maybe there's a force applied down here. 100 pounds. Some dimensions here. This length is 18 inches, and this length of the wall is 16 inches. Just making some numbers up. Okay? Let's find the reaction forces at A that make this body be in equilibrium. So I say satisfy equilibrium. I mean, what we're doing here is obviously this body is fixed, so it's not accelerating. So the reaction forces you can find at A because they have to put the body in equilibrium. So I mean, it's not like an abstract concept where we're satisfying equilibrium. I mean, that's the tool that we use to find the reaction force. Okay? Now, this is not a free body diagram. So let me digress a little bit, do a little aside about free body diagrams. That's not a free body diagram. I see a lot of times students doing these things on exams, problems that I collect, and it's problematic. It often gets them to a point where they get the wrong answer, and time giving partial credit on the free body diagram is incorrect. Why is this one incorrect? This one's incorrect because I'm not showing all the forces of the body. I am showing constraints here, okay? So I'm showing the constraint there that it's fixed. It's not a free body diagram. And then by just putting some force arrows here doesn't work either. All right? So you have to redraw the body, whatever it is. With the externally applied forces, but also the reaction forces. Now, in this case, we have some reaction forces at A. They're unknown. There's some force vector at A, and there's also some moment vector. Right? Now I'm drawing those in red. Those are actual vectors. Okay? This force here, I could draw it right as a vector. Well, technically, if I want to write this as a vector, I should not write it in this manner. I should write it as 100 pounds acting in minus k direction, where k is the unit vector. K, J, I. Okay? Probably used to seeing it that way, so it's this unit vector hat on top. Okay? Now that's a proper vector. You can see it has a direction associated with it. Okay? Now, you don't always have to do that. We'll talk about 2D summations a little bit later on, but for now, technically, if you're doing 3D problems, that's what you need to do. Okay, that's consistent. Right? Now, what makes this a free body diagram is that we've drawn the reaction forces. Okay? Another way you could do it, this would also be acceptable. If I drew it like this, and I just put the scalar values, this is also acceptable. I don't have the minus k vector on here, but the direction's noted by the fact that we have the vector orientation. Now, the force has an x, y, and z component to it. All right? So I'll consider FA and breaking it up into its x, y, and z components. So I have FA x direction, FA the y direction, FA z direction. Likewise, the moments will also have color, x, y, and z components. Okay? There's the moment vector. Well, there's the moment. All right? So we also have a moment at A in the x direction, moment at A in the y direction, and a moment at A in the z direction. Okay? So this is showing the scalar components. This is writing the vector components. Now, for 3D problems, I actually find this approach easier. When we do 2D problems or 1D problems, it's probably easier just to write the scalar components. You can do whichever you feel like. I mean, if you get really comfortable with this, you can always do this. This will always work. This will always work. Okay? But it'll work. All right? These are both correct free body diagrams. All right? Those are fine. This is incorrect. Okay? But here I've clearly labeled all the forces acting on this body. Right? External force, and then I have the reaction forces from the constraint. Whether I've drawn them as vectors or as the scalar components in the directions. Okay? Either way is fine. The other thing to note is that, well, be careful of units, right? So notice I keep the units in here, both situations. And the other thing that's important is assuming direction, all right? So a lot of times students worry about which way should the reaction forces go. In fact, it does not matter, right? For simple problems, you can figure it out. For more complex problems, you might be able to. There are statically indeterminate problems, which we'll talk about in this class, where you will not be able to figure out the orientation. And what I'm saying now is it does you no good to worry about which way the reaction force goes when you draw the free body diagram. It's just a waste of time. it all comes out in the wash anyway. What I recommend, what I do, is you can see I've drawn the components in the positive x, y, and z direction. So for all external reaction forces, I recommend that you draw them in the positive sense. You don't have to. As long as you're consistent, it'll work out. But I just find that easier. Don't waste your time trying to worry about which way they should go. I used to questions in the class when problems. Should it go the other way? It doesn't matter. If it goes the other way, when you solve for the values, you get a minus sign, and it will tell you. Okay? So you don't have to worry about it. Right? It's just something else to confuse you, I think. But these are both appropriate. Okay? Let's look at this one for now. Now this one, I drew it as a vector. I don't really know the magnitude or the direction, so I just kind of drew it in arbitrary directions. All right. So let's look at this approach, okay? The 3D approach first. Okay. So in this situation, let's do the equilibrium equations. So we have the first one is the vector sum of forces is equal to 0. So when we do this approach, we have to make sure to write all the forces as vectors. Okay? So what are the sum of the forces we have? Well, we have FA. I don't know anything about that other than the fact that that's some magnitude direction. The other thing we have is this force, minus 100 pounds in the k direction. All right? So this is a proper vector. Don't put the k here. It's incorrect. This goes to 0. All right? So writing something like this, this is incorrect. It's meaningless because this is a scalar, this is a scalar, this is a vector. You can't add a scalar to a vector. It doesn't work. Okay? You have to make sure you have the unit vectors here on the forces, right? And likewise, if it goes to 0, it's not a scalar 0, it's a vector 0. All right. So now from this one, the answer is right here. It's quite trivial. Right? You take this and solve for FA. You see that FA is simply equal to 100 pounds in the k direction. So it has no I component and no j component. It does, they're equal to 0, right? So it only has a component in the z direction, it's 100 pounds. You probably could have gotten that by inspection. Right. Now what about sum of moments? So if you do the sum of moments, all right. Now remember, when we do the moments, they have to be with respect to a point. And this is from statics. So if we have some point O, and then a force vector. Now, force vectors are what we call like bound vectors, right? They're applied at some other point. They physically are applied at a point. Okay? This might be part of some body, right? That we're trying to equilibrate. Okay? Now, we draw a vector from point O to the point where the force is applied. This we're going to call R. Right? That's R from O to the point of application of F. It can't go the other way. It has to go from O to the point of application. Now the moment of F about point O, so I put the O up here, is equal to R cross F. Okay? And so that'll be the moment vector. All right? This does not need to be a right angle. This could be any angle. Okay? It doesn't have to be a right angle. Okay? Cross product takes into account all that stuff. Okay? It gives you the sign there. Okay? So with that, let's do sum of moments about point A for this problem. Okay? Summer moments about point A. That's equal to 0. Okay, so what do we have? Well, we have at point A, I have the reaction moment, MA. That I don't know. And that vector we don't know. We have that. Now this force here is applied at point A. So its reaction arm is 0. So in other words, there is no moment, right? FA is at the point, so there is no moment. So that doesn't do anything. If you want to technically say it's 0 cross FA, right? But that obviously is going to go to 0, so it doesn't do anything. And then we have this vector. All right. So the vector that we can draw to go from A to the point of application of this force, the tip force, right, is R. That's going to be, well, we go back to this diagram. Back here. Goes 10 inches in the I direction, and then 18 inches in the J direction. So this is 10 inches in the I direction plus 18 inches in the J direction. Remember, I have units. Okay? So that's actually that position vector. So the moment that it develops from this force about point A is going to be R, which is 10 inches in the I direction, plus 18 inches in the J direction, cross the force, which is minus 100 pounds in K direction. That has to equal 0. Don't forget the wiggle on the 0. So now again, we can solve for MA. MA is just simply going to be equal. Let's bring this to the other side, or to the right-hand side. So this minus here, now that can become a positive. So this is just going to become 10 inches I plus 18 inches J cross 100 pounds in the K direction. Now remember, the order of the cross product matters. R cross F is not equal to F cross R. Okay? So this is the order, right? But you can pull a -1 scalar out. All right. So now, when we do the cross product, okay, we can take. It's basically like the product rule for the components. Okay? So we cross this with this, and then we add to it the cross this and this. Okay? So the first component is 10 inches times 100 pounds. So that gives me 1,000 pound inches. And I cross K is minus J. I cross K by the right hand rule minus J. Now we have the term that comes from the 18 cross from this term. So that's plus 1,800. Again, it's in pound inches. And J cross K. J cross K is positive. So that's our vector, right? That's our result. So MA, it has two components. It's got 1,800 pound inches in the I direction, and minus 1,000 pound inches in the J direction. So that's it. Okay? So if you were to actually label this on a 3-by diagram, you would have the 100 pounds acting down. We know that the force here is 100 pounds acting up. That's the reaction force from FA. And then the moment, if we look at the moment components, we have an I component. That's 100-pound inches, and then a minus j component. So the minus j component is going to go in this direction. Of 1,000 pound inches. You still have to draw a double arrow because you know that's a moment and not a vector, okay? And that would be an answer, okay? That's using a 3D approach. Okay. Now, if you look at this, a lot of times we also have simpler 2D types of problems. Maybe the picture gets drawn as follows. As simple as this. Let's put 20 pounds active down. Call this the x direction. This is the y direction. This is fixed here, so again, it's not a proper free body diagram. I'll call this point A, and let's here 24 inches. Okay, so again, find the reaction forces at point A. Now, this is a simplified problem. A lot of the problems we see in this class kind of look like this. This is basically a two-dimensional problem. On these, very often it's simpler to, instead of solving the vector equations, to note that this only occurs in the xy plane. So just deal with sum of forces in the x, and the y equal to 0, and then some moments about the z-axis. That's the moment of the plane, right? So that's what gives us a positive moment sense, right? Because that's the z-axis coming out of the plane, right? What this is basically saying is that if you were to look at sum of forces in the z direction, which is what we're missing here, it's truly 0 because there are no external forces in the z direction. And likewise, there's nothing that gives you a moment about the x or y axis. That's about it. Okay? You basically get like 0. All these equations will be 0 equals 0. You could write this as 120 in the minus j direction, but so you can solve this in the 3D-dimensional manner. But usually we do this in 2D. So this implies this reduced set of scalar equations, really just 3 equations, as opposed to the 6 scalar equations before. I guess I didn't mention that. When we do vector sum of forces, that's a single vector equation, for simple moments. That implies, each one of those implies 3 scalar equations, right? 3 scalar equations, 3 scalar equations. So equilibrium is 2 vector equations, or 6 scalar equations. Now in this situation, what I'm saying is 3 of those scalar equations are trivial. Sum of forces in the z, sum of moments about the x-axis, and sum of moments about the y-axis. Okay? All right. Again, this is not a free body diagram. So redraw it. Right? Redraw the free body diagram as follows. We have the 100 pound, oops, sorry, the 120 pounds acting down. And then we're going to have some reaction forces, x in y direction at point A. Now again, we can look at this and obviously this is going to go to 0. And this is acting in this direction. But I'm just drawing them in general. I've drawn them in the positive x and y direction just to keep it consistent. If that's not the correct direction, I'm going to sign change on the numbers. And then since it's built in, it's fixed. It's not just simply pinned. There's also a moment. Okay. So I have 1, 2, 3 scalar unknowns from the support. Okay? Solve it. 3 equations. So if we do sum of forces in the x direction equal to 0, that gives me just that F(A)x is equal to 0, which we kind of do by inspection. Do sum of forces in the y direction equal to 0, that gives me F(A)y minus 120 pounds. Again, don't forget the units. Equals 0, or in other words, F(A)y is equal to 120 pounds. And then finally, sum of moments equals 0. Okay, now we have to pick a point, so let's pick this point A. Right? It doesn't matter which point you pick. You can pick this point, you can pick the midpoint, you can pick any point you want. Pick one point and do sum of moments. Now, I chose A because what's it going to do? It's going to eliminate the moment due to F(A)x and F(A)y. So I don't have to worry about this. I only get a moment from this force. So it makes my equations go real simple. Right? So this gives me MA. I've drawn that in the positive direction. Now, this produces a negative moment. So it's a negative 120 pounds. And now its moment arc is 24 inches. Right, don't drop the units. This is 0. So this tells me that MA is now equal to 120 times 24. So that's 360. Yeah, that's right. Yeah, that's right. I have a cold today, so let's check. Do that. Sorry. 28 pounds. Okay. Now, remember, in this situation, when we're doing these moments, when you do the scalar ones, very often you get its moment arm. You multiply by it. Now, in this situation, you do have to pick the moment arm that is perpendicular. Okay? So it's this distance. Right? It's perpendicular to the line of force. Right? If you have a force at some angle, there's two ways you can do this. One is technically compute this distance. This is 100 pounds. Figure out this distance is 5 inches. Then this moment would be 500 pound inches. This is the moment that's perpendicular to the line of action. Typically, what you would do, the easier approach, what I would find easier, is just to break this up into its components. Maybe it's a 3, 4, 5 triangle. So this would be 60 pounds. It's 40 pounds that way, right? I'm writing small, sorry. It's 60, 40. And so this one has a moment of 0. And then this one, you would take the moment from that one, right? This distance times 40. Okay? So that's the way to do it. But make sure you get the perpendicular distance, right? When you do the scalar summations. I mean, you can get the same thing by doing arc across F, but it's a little bit tricky. So that's the equilibrium equations. All right. Sum of forces and sum of moments. They can be either vector or scalar form. When you're doing 2D or 1D, probably the scalar form is easier. If you're doing 3D problems, I tend to prefer 3D form, but you can do the 2D scalar approach. I mean, the 3D scalar equations if you wish. I find that a little more difficult. If you do the vector approach, the 3D vector approach, be careful about keeping your unit vectors, making sure you're not adding scalars to vectors, and making sure you are clear in your head how to compute the moment. Make sure you're clear how to compute the moment of the force about a point. Also, again, and I'll emphasize this in other talks, free body diagrams, Make sure you spend time carefully and clearly drawing free body diagrams. I'll say this I'll probably repeat it again. When you do an exam, please be neat, especially about free body diagrams and especially about the basic equations, right? You need to really, if you're doing this problem, to clearly draw the free body diagram, and clearly write at least the first line of the sum of forces and the sum of moments. When you go through and you hash through the algebra, you're a little more lax with that stuff. But what's most important that I see that you clearly have done this and done this step. The rest of it's algebra. Okay? So please do this neatly. Free body diagrams do not contain constraints. They only contain forces. Okay? Only forces. All right? Okay.